Hello everybody and welcome to my presentation with the topic High Fidelity Modeling of Traffic Light Control with XML Logic Representation. My name is Mike Halbach and I am a researching assistant at the German Aerospace Center at the Institute of Transportation Systems, and I have worked on this topic with my colleague Jakob Erdmann. This will be the presentation outline. First, a short motivation why we are working on this topic. Then I want to show you different approach to model a traffic light control in SUMO. In the following, I want to show you some information about the new configuration approach and also how to use this approach. And in the end, I want to tell you something about our replication study. Traffic lights are important elements of the urban area, and they enable efficient crossing of different traffic flows at grade. Therefore, an accurate representation within a simulation is necessary to achieve good agreements between the real-world traffic and the simulation traffic. And so the final goal should be to use and implement all available information from a traffic light control in detail in a simulation. But this is always challenging because in reality there are always limits like time, facility or information to do so, and we want to present you an approach to get a little bit closer to the desired final goal, to model traffic light easily in SUMO. In the past, there were only two ways to model a traffic light control in SUMO. The first way is to use the default generated algorithms from SUMO. So this could be fixed cycle time, fixed controls, as well as adaptive traffic light controls. And it will be a very easy way to model a traffic light, but it will be probably not in the same control logic like in reality. A second way for fine-grained modeling of traffic light control switching behavior, there could be used an external process via Tracy, and here it's possible to model every possible rudiment out of the traffic light logic with different programming languages. And this approach needs a programming experience. We developed a new configuration approach for XML files to model traffic light control, and this new approach have advantages adverse to the two existing approach to model the traffic light. First, it's now possible to model an XML control algorithm which differs from the default algorithms. You do not need a process coupling, which make your simulation faster and simpler. And the new approach simplified and standardized the algorithm description compared to the unconstrained Tracy code. And it's now possible to do a graphical analysis of your operating control with this SUMO GUI. And in the following slides, I want to show you briefly how to model traffic light control in the XML file with the new configuration approach. First of all, the infrastructure and all infrastructure elements has to be modeled with NetEdit. Second, we have to model the signal plan. So every possible signal patterns, including stages and interstages, and this could be automatically with OZIT file and the aid of the function sumo to OZIT, or it could be done by hand with NetEdit. And now we have predefined the infrastructure as well as the signal plan, and this information could be used in the XML file for the control. Now I want to show you something about the new syntax which is now available in the XML file. First, it could be used operators, so comparators or mathematical operators, like in every normal programming language. Additional features are predefined functions. These functions could be used to get information about infrastructure elements, This could be information about detectors. So, for example, a time gap between a vehicle headway or a demand of a specific detector. And it's also possible to get information about a specific link, about the already operating green time or wet time, for example. And another function give information about the current cycle second. Therefore, it's necessary to define the parameter cycle time in the dedicated and in the dedicated value that the cycle that the control is a cycle time based control. And now all operators and functions could be combined and used in the three following expressions. The control could use the information out of the expression for the decision process of the next signal patterns. The first expression is a logical condition. A logical condition could be true and false. And with this expression, it's, for example, possible to model a question block out of a phase logic or to define constants and parameters for the control. Another expression is assignment. Assignment could be used to model an action block out of a phase logic, and the main function is storing and modifying custom data within the XML control. Yes, and one more expression is a function. When a set of logical elements is used repeatedly, it is possible to define these elements within a function with input arguments and output arguments. And so the function simplifies the reuse of a small logic, for example. This will be the new syntax, and which is now which could now access in the XML file for everybody who is well familiar with traffic light logics, as well as SUMO traffic light implementation in the XML file. I want to present you a short two different approach to model a phase logic with the new approach. Yes, the first example is a phase with constant time bounds. Here you could see the logic of phase 1, and below is the XML implementation. And we identified that all important time bounds are constant time bounds, so fixed values. For example, min duration and max duration will be compared with the already operating phase duration. Earliest end and latest end will be compared with the already operating cycle second. So these two values are values for coordination, for example. And now the constant values within the yellow area could define directly in the XML file in the stage 1, which you could see here. And the expression next with the value 1 and 2 defines in which following phase the control could, SUMO phase, the control could go after the stage 1. So here it's possible to go in the SUMO phase 1 and 2, and so in the two different interstages here. And then the control check the expression early target and final target of the mentioned phases next. And with this information here, the control decide in which following phase SUMO could go after stage 1. Some additional information to the two expressions here. Early target will be checked if both minimal time bounds are true, so min duration has to be true and earliest end has to be true. Then the control will check, for example, in the blue area, if a path is true and applies to an interstage action block, then the control will be operated this interstage as the following phase. And final target will be checked if one of the maximal time bounds is true, so max duration has to be true or latest end has to be true, and then the control will check if a defined path within the wet area here, for example, is true and applies to an interstage action block. And then the concerned interstage will be operated as the following phase. So this will be one way to model a phase logic. I have another example. It's a phase logic with variable time bounds. Here you could see that the time bounds are complex conditions. So we have to use a different approach. And the approach is much simpler, like the first one, and it's like a blindy version to transcribe all logic elements. First we have to define every question block from the phase logic in a condition, so block B1 up to block B7, which you could see here. Then we define the path through the logic to each action block which access an interstage. In this case, the path to the block B8 and the interstage 1.2 is that B1 has to be true and B2 has to be false. And then we have the path to the action block, and the same principle we do also to all the other interstage action blocks. Then let's have a look in the XML file. Here for stage 1, we defined the expression min duration with 0, max duration with a very huge number, or we could also omit max dur. It will be the same principle like a huge figure. We choose the two expressions that way because we want to accomplish that the control checked every second the expression early targets from the mentioned phases in next. And then we write the defined path to every interstage action block in the expression early target, first for the interstage 1.2, and then the same principle for the other two action blocks to this interstage. And now we have modeled a phase logic with variable time bounds. This is everything I want to tell you briefly about phase modeling. Let's have a look on our replication study. We have modeled a signalized intersection out of Ingolstadt with our new configuration approach for the researching project SafeNow. And with the aid of a traffic light record, we confronted the SUMO traffic light with the same traffic situations like in reality. And we simulated 60 minutes and compared the second by second sequence of the stages and interstages from the reality with the corresponding sequence from our simulation. And in our experiment, the stages and interstages were reproduced with an accuracy of 96%. And due to time constraints and some of the functions referenced to the traffic light document were not available, we couldn't test code for change in signal programs, bus and emergency vehicle prioritization. But nevertheless, we are convinced that every logic or function could be rebuilt in SUMO as long as the behavior description is available in full. I have prepared also a little video for you. It shows the intersection out of Ingolstadt. On the right side, you see the SUMO net with all infrastructure elements and the traffic. On the left side, you see the traffic mode from SUMO. So you could see the signal patterns and so the state of each signal. In the middle, you can see the occupancy of each detector, and below is the state of each defined condition, if a condition is true, false, or have a specific value. Yes, this is everything I want to tell you about our topic, and thank you for your attention, and I will be here to answer your questions.